Welcome to the second lesson in our study of discrete mathematics, the binomial theorem. In this lesson, we'll build on our study of combinations to make a connection between combinatorics and algebra, specifically to expand binomials. I think I need to motivate you a little bit to appreciate what we'll be doing today. There's a spot in your booklet to expand this binomial, 2x plus y to the fourth power, using a distributive property. Remember, a plus b squared is the same as a plus b times a plus b, so that'll help you expand 2x plus y to the fourth. And you could use the FOIL method or a more visual way, the Punnett square method. All right, so pause now and then press play when you're ready. Okay, you didn't actually need to go all the way, but if you did, way to go. You'll appreciate what we're doing today a bit more. But for some of you, that was definitely not fun. The good thing is this section will give us an easier way to do these types of calculations. Let's learn that way then. Before we get too formal, let's explore the binomial coefficients together. On the left column, you see these binomials raised to a power. On the right side, you see the expansion of these binomials that looks like a triangle. All right, we're going to need your calculator for this, so if you can grab that, and we'll use that. But to explain this visual a little bit more, a plus b raised to the 0 power is 1. Anything raised to the 0 is 1. Then a plus b to the 1 is simply a plus b, but notice there's a b to the 0 and an a to the 0, which is just 1. And then a plus b squared, we can do that. A squared plus 2ab plus b squared, and there's a b to the 0 and an a to the 0 in there. All that information is added in to show this pattern. Notice the pattern on the far left, we have all ones. And the pattern on the far right, the coefficients are all ones. And the powers increase for b on the far right, and the powers increase for a on the far left. Now when we get to the fourth row, which is a plus b to the third, things start to get a little dicey. So let's see why that's the case. Notice there are coefficients in every single expansion. What we're going to do in step 1 is compute 3c0, 3c1, 3c2, 3c3. All right, so on your graphing calculator, enter 3 on your main screen, and then math, arrow right to prob, and then go down to NCR. And then I want you to enter the 0. Press enter. We have a 1. Okay, great. You could press second enter and then change the 0 to a 1. And then do that for 2 and 3. And what you should see is that you get 4 numbers. Those 4 numbers are 1, 3, 3, 1. And the question is, where can you find these numbers in the expansions above? All right, I see them in the fourth column. The power of 3. Okay, so that's that 3 in the combination, 3c0, 3c1. All right, let's move on. Number 2. This expression here, 4c0, 1, 2, 3, 4. Let me show you how to enter that. All right, now type 4 on your calculator and press math and go to probability NCR. Instead of entering all those individually, we could enter them together. I want you to use the brace button, which is second open parentheses. It's in the middle of your calculator. Then type in 0, comma, 1, comma, 2, comma, 3, comma, 4. Close the brace and then press enter. If you didn't quite get all that, you could rewind, but the braces are second parentheses. So you'll get an error if you don't use the braces, because it's a list. So your answer shows up as a list. And that list is 1, 4, 6, 4, 1. Hey, where do we see those numbers in the expansion above? Row 5. Or the binomial raised to the fourth power, which is the 4 and the 4c whatever. One more just to complete the pattern. Now let's do 5c and all those numbers. So 5, back to probability, NCR. And then second parentheses, 0, comma, 1, comma, 2, comma, 3, comma, 4, comma, 5. Second close parentheses with the brace. Now we get more numbers. We get 6 numbers instead of 5. So if we raise something to the 5th power, we get 6 terms. Notice the triangle above, there are 6 terms. And those coefficients, or those numbers that we get in the list, are the coefficients of the variables in the expansion. Notice that while you learned a few new buttons on your calculator, the braces and the comma, we also learned something pretty amazing, that we could expand a binomial using what we learned in combinatorics. That's pretty cool. You might be wondering, why are the values of NCR coefficients of the expansions? If you're not wondering about that, don't worry about this slide. But the expansion of a plus b to the n consists of all possible products that could be formed by taking one letter, either a or b, or x or y, whatever variable, from each factor a plus b. The number of ways to form the product a to the r times b to the n minus r is exactly the same as the number of ways to choose r factors to contribute an a, since the rest of the factors will not so obviously contribute a b. What this kind of saying is, if you're choosing a, you're not choosing b. So the number of ways to choose r factors from n factors is n choose r. Let's get a little formal with Pascal's triangle. Well, it's more fun than formal. Pascal was born in 1623 in the middle of a scientific revolution. There were lots of mathematicians and philosophers and scientists doing great things. And he died 4 years before calculus was officially invented by Sir Isaac Newton, and Gottfried Leibniz. And, he's not the inventor of Pascal's triangle, even though it bears his name. The Chinese actually invented it years before he was born. Pascal's triangle is to the right there. It starts with a 1 at the top, which is the expansion of a plus b to the 0. Then the coefficients of the next expansion, a plus b to the 1, 1 and 1, 1, 2, 1, 1, 3, 3, 1. And all of the numbers below a certain row can be found by adding the two numbers together. So in the 3rd row, we have 1 and 2 that add up to 3 in the 4th row. And then we have 1 and 3 that add up to 4, and 1 and 4 that add up to 5. The Chinese called this the diagram of the old method for finding 8th and lower powers. Basically, they went up to 8 powers, and they didn't really have a need to go any further. We could expand Pascal's triangle as far as we want to, and we'll get all of the coefficients of the expansions of binomials. Let's get practical by expanding using Pascal's triangle. Here we have x plus y to the 6th power that will expand using Pascal's triangle first. What I like to do whenever I expand using the triangle is I just write out those terms. So I'm creating Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. But we need one more row here, because even though we're raising to the 6th power, we need the 7th row, because the first row is raised to the 0 power. Let's build that 7th row. 1, 6, 15, 20, 15, 6, and 1. Now let's use those coefficients to expand Pascal's triangle. So the first coefficient goes with x to the 6th, y to the 0. Second coefficient goes with x to the 5th, y to the 1. Third coefficient goes with x to the 4th, y to the 2, and so on. Notice that the powers of x and y always add up to 6, even if they're on the far ends. So we have 6 and 0, 0 and 6. And then notice that the coefficients will help us determine how many actual terms there are. Fairly straightforward. Expanding using NCR is just like using Pascal's triangle, just without the visual. In this case, we could go right to your calculator and type the number 6 and go to the math function, or shortcut if you find it, for n choose r. And then we could type in the brace along with 0 up until 6 using commas. When we do that, we get a list of 7 numbers. Again, it's 7 because it's raised to the 6th power, so there are 7 coefficients. And those coefficients are 1, 6, 15, 20, 15, 6, and 1. We just plug those coefficients along with the variables in their powers, starting with x to the 6th and y to the 0. Reduce the powers of x, increase the powers of y until we get y to the 6th at the end, along with that coefficient of 1 at the end. And that's it. Computing binomial coefficients. Isn't that what we just did? Well, in this case, what we're doing is finding a specific binomial coefficient. So here's the example. Find the coefficient of x to the 3rd power in the expansion of x plus y to the 6th. That means if you expand that out, what's the coefficient of x to the 3rd specifically? I don't want all of them. I don't want the entire expansion. I just want that coefficient. So 6 is the n value, 3 is the r value, and we could just go right to the calculator and do 6 choose 3, and that will give us the coefficient of x to the 3rd. Now things change a little bit if we have something like 2x plus 3y to the 6th. That means the official coefficient of x to the 3rd would have to include that already coefficient that's inside the binomial. So again, if it was 2x plus 3y, I think that's what I said, then you'd raise 2 to the 3rd power, and then you'd also have the coefficient that came from 6 choose 3. You'll see that show up later on. The binomial theorem takes into consideration everything we just talked about. For any positive integer n, a plus b raised to the n power can be expanded like so. There's a coefficient of a to the n, and what that is simply n choose 0, which is 1. The next one, n choose 1, well, whatever n is, we're using that to find out that coefficient. If n is 5, 5 choose 1 is whatever that coefficient is. We have a to the n minus 1 times b to the 1. Notice that n minus 1 plus 1 adds up to n. The next term would be a to the n minus 2 times b to the 2. And again, those powers add up to n. And then notice that this middle term, n choose r, the powers, n minus r and r, also add up to n. So every power, every sum of powers of a and b add up to n. And then the final coefficient of b to the n is n choose n, which is 1. If we have 10 terms and we're choosing 10 of them, then there's only one way to do that. Now notice that notation at the bottom of the page there. It says that parentheses n over r literally means n choose r, and it gives you the formula for that again. So the only thing new is the expansion using the binomial theorem in the middle there. Let's learn how to expand a more complicated binomial. Here's our final example. We're expanding z cubed plus 5x squared to the 5th power. All right, now we could just choose any method we want. We could use Pascal's triangle. We could use the NCR option in our calculator to use with that 5th power. But I want to point out the fact that the a term that we're talking about here is z cubed. This is the first time that the term inside the binomial has a power. And then the b term is 5x squared. That's the first time that the term inside of the binomial has a coefficient itself. So then we could use the binomial theorem to expand this out, which again is basically the summary of Pascal's triangle and n choose r. And what that would look like is first finding out what that coefficient of the first term is. And notice that the first term is z cubed raised to the 5th power, which is 15. And that first coefficient is 1. Then let's think about the last term. We have 5x squared raised to the 5th power, and that coefficient is 1. And then we could fill in all the coefficients in the middle. And we're using 5 choose 0, 1, 2, 3, 4, 5 to write out these terms. But that 5x squared also has coefficients for itself. All right, so here's the expansion of z cubed plus 5x squared to the 5th power. Notice how I write all the terms in parentheses first before I consider simplifying in a final step. which I'm not actually going to do here. Let's explore Pascal's triangles a bit more by considering these questions. There are some unique questions about Pascal's triangle for you to consider, totally optional, but the answers are on the next page. I hope you enjoyed learning the binomial theorem with me. I especially like Pascal's triangle. Thanks for watching.